Hi, and welcome to another video in the series to better understand the atomic structure. So today we're going to look at the Rydberg formula. So last time we saw that there are certain things known as spectral lines, which are associated with absorption and emission of specific colors of light, which correspond to specific wavelengths by atoms due to electronic transitions. Now, Rydberg is this guy who gave this formula, which looks something like this. So you have a bunch of terms in here. So delta E is the change in energy, and this refers to the change in energy when an electron jumps from one shell or one energy level to another shell or another energy level. This is the energy gap associated with the shells. This is just a constant, Rydberg's constant. H is known as Planck's constant, which we will look a bit more into soon. C is the speed of light. And N1 and N2 represent the shell's numbers. So you start from shell 1 and you move outwards with increasing N for increasing number of shells. So that's also K, L, M, so on and so forth. Now, as you can see, the jumps of an electron from one shell to another corresponds to a certain energy, which is given by this equation. So we can figure out that given an electron in a shell, let's say electron in n equals 1, we have one electron, and it jumps to a shell n equals 5. Then you just plug it into this formula right here. You plug in 1, you plug in 5, and you plug in the other constants, and you're going to get a value for the change in energy. And this is the energy. Sorry about that. This is the energy absorbed to go from 1 to 5. Now, the reason this is important is because it also tells you what color of light is going to be. Color of light, which can be correlated to either wavelength or frequency, which are two properties which you can look at for any waves, is emitted or absorbed. So the correlation between this and the energy is given by an equation that looks something like this, where energy of a photon, we're going to look at what a photon is given by Planck's constant times frequency. Now this is a very nice equation because up until then people weren't sure what light really is, and Einstein decided to adapt Planck's general equation, this frequency related thing, to a photon, which is a packet of light, which is basically saying that light is basically a bunch of particles called photons. And each photon is associated an energy according to its frequency. Now, we're going to look at how this equation came in the subsequent two videos. So for now, we're going to start using this equation to see what the wavelength or frequency of radiation emitted is. So now we're going to use this E value, this energy of a photon, substitute it into this equation right here. So the change in energy is going to be the energy of the photon that's emitted. So h mu is equal to Rydberg's constant times h times c 1 over n1 squared minus 1 over n2 squared. The h's cancel out. So you are given a relationship for the frequency of light. So the frequency can be written in terms of c over lambda, where lambda is the wavelength, speed of the wave. So this is true for any wave, not necessarily light. Frequency. So using this, we can write c over lambda equals r infinity times c times 1 over n1 squared minus 1 over n2 squared. C's cancel out, and you have a relationship for lambda. 1 over lambda is given by this. So this is essentially telling you what the wavelength or frequency of light emitted is going to be given or absorbed given an electronic transition. Now, these electronic transitions were given very nice names by people who discovered them, and they're given names in terms of the series. So the Lyman series corresponds to any transition from any energy level above 1 down to 1. So that's the energy gap there, that's a bigger energy gap, and so on and so forth. So whenever an electron jumps from an outer shell to the innermost shell, where n equals to 1, the series of radiations of frequencies that you get, series of frequencies or colors, which might be easier, is the Lyman series. Similarly, you have the Balmer series, which corresponds to n equals 2, so emissions of electrons jumping from higher shells to n equals 2. Then you have the Paschen series. Again, same concept, n equals 3, brackets, n equals 4, and so on. So the idea is when you have these electronic transitions, energy is emitted corresponding to this energy gap, and that energy gap is also equal to the energy of photon emitted. And this photon is a packet of light. So if you have an energy gap given by this, you're not going to see two different photons of different energies combining to give this total energy. It's always going to be a single photon that's emitted with a specific frequency. Whose energy is given by E equals h mu, and that's going to be the same energy that's released from this electronic transition. Now we're going to look a bit further into how this equation actually came about, and it's going to delve a bit into what are known as harmonic oscillators. Thank you.